Indeed, I changed the title because I realized that I belong to a community that is, I would not say orthogonal, but I mean at least a borderline to yours. So I decided to give you more the ideas that are driving me toward your field, more than about something that is too technical. And my new title is Inferring Physical Parameters in Turbulence from Nudging to Machine Learning. Indeed, I will say very few words about machine learning, some words about nudging, even though it's a very old technique, I understood. But I mean, I just wanted to convey you what is my driving, at least. And so typically, we started recently to work on applications that are very common and very popular now on the artificial intelligence community. That I dubbed, for instance, I mean, any problem concerning classification, I dubbed it physics inferring, right? That is, you have some sample and you want of some field. In this case, is a cat, and you want to understand if this field belongs to different classes. And or another very important, I don't have to teach to you, issue is what is my understanding of my translation to artificial intelligence community of data assimilation. That is, you have some corrupted image or maybe some measurements only on a subset of your field, and you would like to have an algorithm that gives you the best guess everywhere for different purposes. I come from turbulence. And my way to translate these two problems are the following. For instance, what about physics inferring? I could imagine to have turbulent configuration coming from simulations with experiments with different parameters. These are all configurations coming from turbulence under rotation at a different rotation rate. And you see, some of them are very different from some other. The only difference is the rotation rate. Some are very similar, even though the rotation rate is slightly different, like in this case, rotation rate 5, rotation rate 10. And you would like to understand if there is a simple way to infer this parameter, just looking at the image. So to understand the underlying physics just from the image. For instance, one good question for a machine could be, I give you this set of configuration, classify them in their correct omega class. The class could be coarse, could be refined. I will not enter too much in these details. And the other problem concerning data simulation, on the other hand, is very. I mean, it's has already been discussed here, of course. Is suppose you have field measurements on a subset of points, and give me the reconstructed field. And okay, forget about this. This was for another conference. Sorry. And so just to summarize, what is the bottleneck from our point of view? I mean, from the point of view of turbulent people. Here I give you two famous movies. One about the 2D circulation of the Mediterranean Sea, I mean of the global ocean, indeed. And another is a movie that will show up now in a few minutes about a 3D simulation. And both of these flows are turbulent. And one is mainly 2D, not exactly 2D, but mainly 2D. The other is fully 3D. And we know that they have very different statistical properties, very different structures. And we would like to understand, my point of view is, we would like to understand what is driving the flow from one kind of physics to another one. Because there are situations where the flow is neither 2D nor 3D, and maybe slightly changing one parameter, you switch on from a situation like this, where you accumulate energy to large scales, to a situation like this, like in 3D, where you produce smaller and smaller fluctuations on smaller and smaller scales. This is a 3D simulation where we are zooming inside the flow, and we discover that the flow is indeed a strongly multi-scale. There are structures inside structures, inside structures, inside structures. And indeed, in many situations where we are in between, the flow is neither 2D nor 3D, we do not know how to predict if the main flow will develop like this, or if the main flow will be dominated by this mechanism. And from my point of view, it would be good to have a sort of a probe of the flow configuration to understand what are the driving mechanisms, what are the physical variables, the real key degrees of freedom that play a role in a situation like this. Maybe it's the boundary share, or in a situation like this where we produce smaller and smaller vortex filaments. So what are the bottlenecks? The bottlenecks are mainly two. Again, it's very short recap of turbulence background. The first bottleneck is that, as we know, turbulence in 3D is a highly multi-scale phenomenon. It means that if you look at the spectrum as a function of the wave number, the spectrum has a power law behavior, close to k2 minus 5/3, and the range where you have a power law becomes more and more extended by increasing Reynolds. So there is no hierarchy of degrees of freedom. Having a power law, all degrees of freedom play more or less the same role. So the question is, okay, but I mean, which one are indeed connected to the formation of these structures? And these structures, are them important for the global or for the local statistics, or they are just the tail of the dog and not the head of the dog? And the bottleneck is that the number of degrees of freedom, as we already saw in the previous presentations, grows like the Reynolds number. And for typical turbulent flows, the one that you can develop inside a room like this when there is a fan, the number of degrees of freedom may easily reach the value of 1 billion or 1,000 or trillions. And so there are all degrees of freedom that are active inside the flow, and that we do not really know if there is a hierarchy inside them. If there is some that have a more important physics, some other have a less important physics for the global development. The second bottleneck is this one, is that these degrees of freedom, this huge amount of degrees of freedom that are interacting, indeed produce a strongly non-Gaussian distribution. This is a PDF measured inside a 3D turbulent flow of the acceleration. So the time derivative of the velocity field along one particle trajectory. And the PDF is normalized. The PDF of the acceleration is normalized with its root mean square. And you can easily see that in a stupid turbulent flow, at Reynolds not so high, moreover, you easily find fluctuations that are 30, 40, 50 times the standard deviation. So these degrees of freedom, not only they are billions of them, but they are strongly non-Gaussian with extreme events. I mean, for a Gaussian distribution, the probability to have 40 times the root mean square is 0, right? And we have no way from the equation of motion to predict this PDF. And indeed, we have no way, we don't know what are the key physical ingredients that leads to this kind of empirical observation from the Navier-Stokes equations. Just to give you an idea of how violent the system can be, here I show you the evolution of one particle inside the flow. So this is the velocity along the part, this is time. So I follow the velocity of the particle. You see that most of the time the particle goes around with fluctuations that are more or less Gaussian, and then from time to time enters in extremely high and intense events, which are small tornadoes, and where the velocity starts to fluctuate, the acceleration is even, of course, it's the derivative of this curve, is even more bimodal. But you see, it's not, I mean, this might look as a bimodal distribution, right? One could say, okay, that's easy. Just put a threshold, but there is no bimodality here. It's a continuous of fluctuations, indeed, when you look inside the whole flow. So who are the degrees of freedom that play a role in producing these extreme events? And so why we ask this question? I mean, I'm not working in a weather center. Nobody's paying me for reconstruct the flow variable. So my motivation are mainly on the basic physics. So the question is, I would like to understand the quantity, how much information I have to supply to reconstruct the flow, and the quality. Which information? It's better to measure where vorticity is intense, it's better to measure where the shear is intense, or maybe where we have a very strong acceleration. I mean, can we start to have a classification of the quality and quantity of the information inside a turbulent flow to understand what is driving, what is the head and what is the tail in our dog? So I'm going to show you, I mean, mainly results using nudging. Just to give, there is a movie. There should be a movie, I think. Yeah, and I mean, the kind of question that I will try to ask is, I mean, it's better to measure spatial or temporal evolution, for instance, if we wanted to reconstruct the flow, let me say, or to guess what's happening inside the flow, or how many data I needed to supply to synchronize. I mean, to have a perfect reconstruction in a fully turbulent flow. Fully turbulent, but I mean, it's a sort of idealized situation. I mean, with no, not as complicated as the one that you are attacking in numerical weather prediction. Or, I mean, the other question that was cited by you, I mean, I was very happy. I mean, can we guess velocity by measuring only temperature in convection, right? So it's temperature is active, but there are situations where the buoyancy is not so active at all scales. So maybe you can reconstruct well only large scales if you measure only temperature, but not small scales. These are the kind of questions. Or, I mean, for people coming from fluid dynamics, another important question is the boundary. What is the role of the boundary? I mean, vorticity is mainly inputted in the system by boundaries, and we would like to understand if it is better, I mean, if boundary regions is more important than bulk region. And again, I mean, the long-term goal would be to control. I would like to understand what are the key parameters, such as then I can act on these parameters. I can imagine, for instance, a Lagrangian forcing inside my system. Particles that go around and that here and there do something. Maybe they warm the flow, or they cool the flow. Or, I mean, it's not probably doable on a global atmospheric circulation problem, but there are many turbulent situations where you can indeed things to polymer. Polymer are just stupid, dummy objects, not active. They go inside the flow and they reduce drag of order of magnitude. Right? And just because they absorb the energy, the kinetic energy in the right position, and they deliver the kinetic energy in the right position, and in this way, just by putting polymers inside the flow, you can reduce the drag of order of magnitude. So that's our long-term goal would be to engineer, let's say, smart polymers in some sense, just to understand where to act and what are the key degrees of freedom. So as I said, we did a little bit with machine learning, but this I will not speak about machine learning. If you are interested, I can tell you more. I will speak about nudging. So I will tell you a few words about the classification problem that we played by trying to understand and to infer the right physical parameters by using the equation of motion. And the way we did is, as I said, we set up a simulation that is our truth, our numerical data, that is the one that, I mean, the experimental data we supply, and we extracted information either on a Eulerian grid, on small subset, or on a Fourier filtered flow. So just extracting some information from our truth, and then we used this information and only this information to try to guess what is the right omega in the flow. And we do it by nudging, so I will not tell you what nudging is. And for instance, we do it by just supplying this information and playing in a fair way, I would say, because we do not say anything about the forcing mechanism that have generated the flow. So we don't supply the shear, we don't supply temperature. I mean, in our case, there is no temperature, but I mean, in principle, we don't supply the temperature, we don't supply the steering mechanism. We only supply the data. And we evolve the equation, another equation, a twin simulation, by scanning omega and seeing what is the optimal omega that allows me to synchronize with my input. And in this way, we were able to get, I mean, a very precise measurements of the omega, just to give you an idea of how things work. Here I show the reference. Here I show 3 nudged simulation at 3 different omega. This is the right omega, the one that was used for the reference that I supposed to not know. And these are 2 different omega. Of course, I mean, in one case, the flow is very different. In the other case, it's very difficult to compare. But if you implement nudging and you measure the error in terms of the L2 norm between the Fourier modes, you are able to, this is the spectrum of the error. So this is telling you how much you are able to reconstruct your flow at different scales. And you see that where you nudge, so where you supply the information, when you guess the right omega, the error is order of magnitude smaller than when you use the wrong omega. And indeed, when you nudge with the right omega, you are also able to reconstruct outside your nudging frequency. So you propagate the information at smaller scales. And if you want to be more quantitative, you can do it, you can write one number that is the total integral of the L2 norm at all frequencies, at all wave numbers, sorry. And here I give you the error as a function of the omega. Forget about the shear, it's another problem. We scan the different omega, and I show the error as a function of omega over omega f, that is my guess. And you see that the error goes down of 3 order of magnitudes when we guess the right omega. I mean, we tried other methods, not based on data reconstruction, but on, I mean, correlations, cross correlations, and things like that. I mean, the quality of the reconstruction, the deepness of this dip was much lower. Then let me say a few words about the synchronization problem, not inferring the physics, not reconstructing the parameters of my data, the main, in this case, the rotation of my data, but I mean trying to reconstruct the flow. And we mainly compared 3 different quality of information. So the same number of inputs, but we provided inputs in a Eulerian grid. So suppose that you have anemometers in your flow, measure the velocity, on a Lagrangian grid, which means following particles, same number of points, but just following particles, so exploiting also the temporal correlation of the flow, or in Fourier. So just, selecting, this was, I don't know, 100,000 degrees of freedom, we select 100,000 wave numbers. And so we had the same number of inputs. We wanted to understand if these 3 guys give us different outputs about the reconstruction. And again, we played in a fair way. That is, we produce our data with a direct omega simulation with some forcing, but when we nudge, we don't put the forcing. So we really put only the information that we have from the field. We don't suppose to know what has produced that particular flow. So without the nudging, the flow would die because there is no input of energy. It would just go to 0. So all what we see is the results of what we measure. No other. The information is that we know the equation of motion, of course. I mean, we know the Navier-Stokes equation. And just to give you an example, this is again. This is the spectrum of my flow, and let me just discuss, for instance, this figure. Here I show you the spectrum of my nudging field. So this is what this was an Eulerian nudging. So we put anemometers in my flow, and I look how much energy, how much energetic the information is. So I look at my input field where it's putting information as a function of frequencies, and it has this spectrum. You see, most of the information is at a typical scale that is the distance between the anemometers, the inverse of the distance between the anemometers. And then we have the black line is the truth, the spectrum of the truth, and the orange line is the spectrum of my reconstructed field. No surprise, in some sense. I reconstructed the physics very well, because I give the right forcing in some sense. I give some input. But what is interesting is that not only is the physics is reconstructed, but it's reconstructed point-wise, because here I show you the point-to-point error. This is the sorry, I should have put. Okay, yes. I show there also this spectrum. So the spectrum of the difference between my input and my output. I mean, what I give and what I reconstruct. And this depends on the point-to-point structure of my flow, depends on correlation inside the flow. And look at the error. The error is really small. So I mean, this was 20% volume nudging, and we were able to reconstruct almost perfectly the flow everywhere. This is a sort of synchronization to the whole data. If you use less percentage, 5%, then the reconstruction is less good. There are errors at small scales. You cannot beat the chaoticity in space of your flow. This is a summary of total reconstruction quality. I show you here the correlation between my reference and my reconstructed flow. So normalized, such that this is between 0 and 1. 1, it means that I have, this is the correlation in space, the full space correlation. So it's 1, it means that I have synchronized the reference data even outside the region where I nudge. So I fully reconstructed my flow like this. And this is for the velocity field, and this is a small scale observable because it's the same quantity but measured with the vorticity, so it's 1 gradient more. And so when this guy is 1, you have synchronized to the data. When this guy is 1, you have synchronized to the data also at small scales. And the curve, I mean, forget about that. There are many curves here. What is, let's fix at 1, which is given for one given nudging parameter. And you see that both the energy, the large scale, and the small scales, the entropy, for a percentage of the order of 20%, you are able to fully synchronize with the data. And indeed, you are better than guessing also when you didn't synchronize, because this is just the straight line, trivial reconstruction that you would guess by doing linear interpolation in your flow. So I mean, all the difference between here and here is induced by the equation of motion and by the correlation induced by the equation of motion. Then you can measure other things. You can measure the PDF of the error. This is another important, another important point, because we know that there are strong fluctuations. So for instance, here I show you the point-to-point error PDF in the whole volume. So I go point by point inside my 3D volume, and I measure the difference between my reconstructed flow and the nudged, and the truth, because I'm in the whole volume. And you see that this is the mean value of the velocity, and you see that the errors are nevertheless always much smaller than the mean value, and then you can eventually quantify how good your reconstruction is by extracting a posteriori also an estimate of your error. Here is the comparison between Lagrangian and the Eulerian that I promised at the beginning. So this is again the parameter that when it is 1, I synchronize to the whole in the whole volume, and the circle are the Eulerian anemometers. The green things are the Lagrangian ones, and you see that for concerning measurements of the large scale properties, the energy, the two are independent. When you look at the small scales properties, that is the vorticity, I think are the empty circle here, the two have a slightly different performance. I'm almost finished. One message more, sorry. We tried also this nudging in other situations, in particular in the presence of rotation. In the presence of rotation, the flow is much easier to guess, because rotation is inducing strong correlation in your flow. And there we saw that by applying exactly the same protocol of before, now the ability to synchronize happens at a much smaller percentage of information provided. So let me. Okay, this was about the Fourier. This was about the Fourier things. Maybe I will skip. Let me go to the conclusion and trying to recap what is the message. So the message is that we were driven and we are still driven by the need to understand. For instance, this is a simulation of a Rayleigh-Bernard cell, and this is so here it's a cell that is heated from below and cooled from above. So you have the typical convective structures. These are pretty high Rayleigh, so the system is highly turbulent inside, right? And this is the truth. And this is, for instance, a nudged simulation obtained by nudging along Lagrangian trajectory. So we have particles that go around, and we suppose they measure only temperature, so they measure only the forcing. And out of these temperature measurements, we perform a numerical simulation by just plugging the right temperature where the particle is, and we try to reconstruct the whole flow. So this is just the first step. The kind of question again that I would like to understand is, for instance, is it better to have tracer neutral particles that by definition they go everywhere, or maybe it's better to have particles that have some inertia, some probes that have inertia, because inertia will correlate with the structure of the flow. For instance, if you have light particles, they will tend to go inside the vortex filaments. And vortex structures in Rayleigh-Bernard means plumes. So maybe with the same number of objects, but inertial, you might have an information that is better to reconstruct because you preferentially sample structures inside your flow instead of throwing buoys that go everywhere. Or maybe again, in Rayleigh-Bernard, it's easy to guess that if you have a fixed anemometers and you have a fixed number of them, it will be better to put them in the boundaries than in the center. I mean, if you measure temperature in the center only, there is no way to guess what is the running Rayleigh number inside your cell. Because inside the center, the temperature profile is always flat, independently of the Rayleigh number. So if you measure temperature only in the center, out of the temperature, there is no way to guess what is the Rayleigh number. If you measure temperature only in the center and you nudge, then you use the equation of motion. Inside, you also build the right velocity correlation, and then you can guess the right Rayleigh number, because the correlation between velocity and temperature depends on Rayleigh. Okay, so this is the idea that we have in mind, and of course, I mean, I'm here because I want to learn about other methods to assimilate data, because they might be more efficient, and it would be great if there is anybody that wants to collaborate with us in fixing, a very simple but paradigmatic turbulent setup, where we know everything about, we know a lot about the physics, we know the spectral properties, we know there are tons of experiments, there are measurements from hundreds of different groups, numerics experiments, and trying to see how much for a system like this, where we can fine-tune the intensity of the turbulence, fine-tunes the importance of temperature, compare different data assimilation tools. And I think I stop here. Thank you very much.
Thank you very much.
Welcome.
Yes?
I'm Italian, I can speak loud.
No.
You can use your hands.
You have to be recorded. You cannot be loud.
So Luca, this is more just to understand better the experimental setup, because you say that you remove completely the forcing when you run your your nudge trajectory. So this means that you are in the context of the generalized synchronization, right? So there is model error here in a way.
Yes.
And when you say that nudge 10% there, you mentioned that it was a Lagrangian observation, right?
Yes.
And these are advected by the flow.
Yes.
They don't have inertia there, right?
No.
So does it mean also that they may end up to be concentrated all together in the same place, or they?
No, because if they are tracers, they explore the whole volume. The flow is incompressible, so they will go around everywhere. And indeed they do. These are point-like measurements. It's like I'm supposed to have a probe that is very small inside my flow. But for instance, in this case, just to stress again that we don't use the forcing, in the reconstructed flow, we do not supply the temperature on the boundaries. So the information comes only through the temperature measured by the flow. While, of course, in the truth, there is temperature on the boundaries, because otherwise the flow does not start. And also I have to add another relatively important information, that is, when I say 10%, in this case, indeed, it's much less, because it's 10% volume-wise, but because my probe is a point, I get the 10% just because I spread the information on a small volume around the probe. But indeed, I mean, really, if you consider the degrees of freedom, it's much less than 10%.
But it's a perfect data.
Yes, it's the perfect data. When I supply, it's the perfect data, yes.
Okay, thank you for this very, very nice talk. I just want to, so imagine that you want to make a forecast now with your system. So could you rebuild the forcing based on your analysis?
Yes, but the forecast will not be, I mean, it will not be improved in some sense. I mean, I can use the last time configuration obtained from this mechanism to do the forecast. But then, I mean, I must have a good model to do the forecast. That's.
You cannot infer the forcing, I would say, of the system, the true forcing.
In some sense, I can do it. I mean, this is the well. To infer the forcing is not so. In this way, it's not possible. I should have a parameterization of the forcing, and then fine tuning. I should have combined the two results, the inferring of the physics and these things, right? So I should have a parameterization of my forcing and infer the right parameters of the forcing. Then I could do it. Yes.
If I may also ask a question, I mean, I've been involved with some of the experiments in the rotating annulus of both kinds, thermally driven and the barotropic animals of Mary Sweeney. So I've been wondering, there are various ways of flow visualization, not just in those experiments, but in anything. So have you thought of using data assimilation really in order to infer the three-dimensional structure of the flow?
Yeah, we are trying to do that. It's a very natural question. No. To do this is my augmented reality word there. Supply an augmented reality flow representation out of a set of measurements. Absolutely.
Okay. Thank you very much.